Good afternoon, everybody. Hey, hopefully you guys are enjoying this nice spring-like weather that we're having. Looks like it's going to be like this for most of the week and through the weekend. So it's a nice reprieve considering a week and a half ago, the high was -1. So, yeah. But anyways, yeah, get outside and enjoy if you can. My patio's finally becoming snow-free, so that's a plus. I might break out the old lawn chair. So anyways, today we're going to look at chapters 7 and 8. Okay, so we'll be covering crustal deformation and mountain building. Okay, and then we're gonna kind of switch gears from a inside Earth type perspective to an outside Earth perspective, which we call surface processes. I don't know why I'm blanking on that. It's my specialty area. Feels like a Monday, but it's a Wednesday. So at some things that happen at our surface. So weathering, soil production, mass wasting. Okay, so just kind of a hodgepodge of different surface processes. So before we get started, are there any questions on anything?
Actually, I have a quick question.
Go ahead.
I was taking the pre-quizzes or the extra credit quizzes or whatever, and there was a question about soil, like erosion and like what prevents soil erosion, and the answers were planting vegetation, removing vegetation, and creating a wind breaker or wind wall or whatever they're called. I thought that both planting vegetation and the wind wall were like effective for that.
Yes, that would be true. I can look at it.
Okay.
So of the two options, which of the two do you think would be the most important?
Probably planting vegetation.
Exactly. Yeah. But I'll take a look at it. We're actually going to talk about that today.
Okay.
So I'll look at it. Soil. Okay. Yeah. If the answer is wrong, if I put in the wrong answer or whatnot, it's easy to change it and update grades. So no worries there. Okay, good. Well, seeing concurrence there on that, so that's a plus. Well, I'm glad to see that you guys are reading the book and getting that information. That's music to my ears. So yeah, I'll see what I can do with the thing. Okay. Okay. So here is the presentation. Let me hide this thing. Well, okay. All right, so we're going to start out talking about mountain building and crustal deformations. So first I'm going to talk about deformation. Now, I want you to know that deformation is different than metamorphism, okay? It's really kind of a gray area where these two meet, as are a lot of things in geology. Nothing seems to ever be perfectly like it should be. But basically, in a nutshell, the difference between deformation, okay, which is just changes to the original form of a rock body, or just a mass of rock, okay? So those changes can occur in forms that metamorphism occurs as well, like changes in temperature and then pressure, okay? But the main difference between deformation and metamorphism here is that deformation occurs at a really small, pretty small scale, whereas metamorphism, as we saw in chapter 3, I believe it is, metamorphism tends to be a large scale process. Hold on just 1 minute, folks. All right, sorry about that. So deformation is pretty localized, small scale. Morphism is usually large scale, okay? And another difference is that deformation, if there is an increased temperature and an increased pressure, it's going to be relatively minor, whereas metamorphism, it can be minor, but often with metamorphism, the temperature and the pressure are quite a bit higher, okay? So those are the main differences, just so you can understand what the difference between deformation and metamorphism is. Okay, just like metamorphism, deformation can occur in any type of rock. Okay? It can even occur with metamorphic rocks. So the main type of deformation is a fold, okay, which is typically viewed. You can see that there's two different types of folds here. Okay, we have an up-arching fold and then a down-arching fold. The up-arching fold is called an anticline. Okay, the down-arching or down-warping one is called a syncline. Okay, they're both formed in the same exact way, from squeezing, basically pressure pushing inward from this side and this side. Okay, so pushing inward from the sides. Why? The reason why it becomes an anticline or a syncline is really just dependent on the individual mechanics of the rock. Okay, maybe the beds are slightly dipping downward, perhaps, which means that they're likely to fold downward when pressure is put against them. But that's nothing that you guys need to specifically know, but you just need to familiarize yourself with the two different types, so the anticline and the syncline. Okay, now if you were to put a mirror down the apex of these folds, so right down the middle, that's called the hinge line, by the way. So if you put a mirror down the middle, if you're going to be looking at the two different limbs, okay, so the limbs are the sides, the two sides that make up the fold itself. So one here, one right here. Let's see. So when you have that mirror down the middle and you look at it, it's either going to be that the two limbs look the same, and in that case, the fold is going to be symmetrical. Okay, symmetrical means just a mirror image on both sides. Okay, so that's right here. That is this is a symmetrical anticline, so not fold. When the limbs don't look the same on both sides, that's asymmetrical. Okay, so in this case, this one is a little bit longer. This side on the right is a little bit steeper. And then there's kind of a little more of an oddity called an overturned limb. That's this, where enough deformation occurs where the top rock structure actually gets bent completely around and tucked underneath the rocks below it. Okay, so that's always an interesting one to see, but it's pretty rare to find those. Okay, so yeah, what we just looked at is kind of like a really small localized type situation. Folding can occur in a little bit larger settings, okay, in which case they're referred to as domes if it's a large anticline. Okay, notice the upward arching rock strata here. And it's a basin if it's a syncline, so it's got the downward arching strata. Okay, so these are just more of a large scale type example of anticlines and synclines. This situation up here is a little bit unique because it doesn't really look much like an anticline, which it is, because what's happening is the surface of the Earth has weathered and eroded away at a different angle at which this anticline has presented itself in relation to a flat surface. And so what you're seeing is kind of like a skewed, cut off, uneven version of an anticline. Okay? I'm going to leave it at that rather than go into more detail and create a lot of chaos and havoc. But basically, if the way you'll know the difference between a dome and a basin is in a dome, the oldest strata is going to show up in the middle. The youngest strata is going to show up on the outside edges. Okay. The basin, it's the exact opposite. The youngest strata is going to show in the middle, and the oldest is going to be on the outside. Okay, so just come back and relook at these pictures at some point before the midterm, and that will help you hopefully get solidify this concept, because I know that trying to visualize this stuff in such a short time frame can be difficult. So definitely come back and relook at this concept. Okay. And actually, are there any questions, I guess, on anything that we've looked at so far? Okay. All right. Then let's go ahead and move on to look at faults. So faults are just simply fractures or cracks that occur in solid rock, okay? And it's those cracks, the faults, basically they separate two different, when they do form, they will separate two different blocks of rock. And one of those blocks is going to move in relation to the other, okay? And that's what you're seeing here. These black arrows represent the direction of movement, okay? So in terms of structure, you have the hanging wall and the foot wall, okay? The foot wall, think of it as it has its foot underneath the hanging wall. So its foot is right here. So the very bottom part of the foot wall is underneath the hanging wall. And then with the hanging wall, it hangs, the top part hangs over, well, it hangs over the foot wall, basically, pretty much everywhere. Okay, so that's how I remember the difference between the two. Okay, so that setup that you're looking at is with what's called a dip-slip fault. Okay, this is just another term to use for the exact same concepts we've been looking at already of that occur at convergent plate boundaries and divergent plate boundaries. Okay, so its name technically is the dip-slip fault. The strike-slip fault is a transform fault where you have the two blocks of rock moving, just sliding past each other. So that means that there's tension involved with this specific type of fault. So that's the San Andreas fault example. Oh, so I guess I already got ahead of myself on the two parts, the hanging wall and the foot wall. Okay, so let's look at the two different type of dip slip faults, okay? The normal fault and the reverse fault, okay? These are concepts that you already know. It's just adding a new name to it, okay? Why that's necessary, I'm not sure, but I think this also probably goes back to the whole Europe versus US tracks of geology early on. So a normal fault is essentially a divergent plate boundary. Okay, it is where you have two plates pulling apart. Okay, and when they pull apart, what emanates is, or what happens is that the hanging wall block moves downward in relation to the footwall block. Thus, the hanging wall, the land above the hanging wall block, looks like a valley, and that valley is called a graben. Okay, so right here is the graben. And then the footwall block typically remains just as it is. It often is the area with the highest relief. So that's called a horst. That's these kind of linear ridges. If you go to Nevada on a east-west viewpoint, if you're driving, it's just series after series of these normal faults. You just keep going up over mountains, down into the valley, up mountain, down valley. It's horrible on the fuel mileage, but it's really cool to see. So definitely worth checking out. Then there's the reverse fault. The reverse fault you already know as a convergent plate boundary. Okay, that's where you have the two plates smashing together. So in this case, you're going to typically have the hanging wall block move upward in relation to the footwall block. Okay. And then lastly, a thrust fault, which isn't as common, but this is just a shallower angle fault where you basically have the hanging wall block rocks on top of the footwall blocks, and the hanging wall block will just essentially move, just keep moving to the right, okay? And so the footwall block just kind of remains stationary usually. The hanging wall block will continue its movement to the right. And then lastly is the strike slip fault. So those are transform faults. Again, the displacement is horizontal. So plates aren't crashing together and they're not pulling apart. Okay, so that's a look at faults. Okay. So now let's look at joints. So joints are not faults. Okay. What a joint is basically just a small fracture or a crack that occurs in solid chunks of rock as a result of, actually it could be for many different reasons. Oftentimes it's because of the movement of Earth's plates. That movement can brittly cause cracks to form within the rocks themselves. But the main thing about joints is that, they don't move. Okay, unlike faults, joints, if they do form, they just stay stationary. Okay, so now that we've gotten all that early information under our belts, let's apply it. Okay, so we're going to talk about mountain building here. So the general term for mountain building is orogenesis. And what you're looking at here in this picture is a typical scenario for mountain building, a convergent plate boundary. So you're seeing the two plates smash together and the land is being driven upward. Okay. Another concept is called continental accretion. So basically, here on the west coast of North America, we have the Pacific Plate and we have the North American Plate. And the Pacific Plate is being subducted beneath the American Plate. And the Pacific Plate is seafloor, as you would expect. And what happens is you have all these tiny little islands, like old volcanic island arcs and whatnot, little volcanic islands out in the Pacific. Because the Pacific plate it's moving all of those islands very slowly to the east, where eventually those little chunks of land will get smashed up against the west coast of the US. Okay, and so all these bright colors you're seeing here represent what's called accretion. It's just all those individual fragments that were smashed up against the western edge of the continent. Another term for these fragments is terrain. Okay, you'll see that as well. But as you can see, a substantial amount of the whole west coast, including most of Alaska, pretty much all of British Columbia, Washington, Oregon, Nevada, and California, all of those places were not, that land is not part of the original North American continent, which is called a craton. Okay, it's this tan area that you're seeing. That's the oldest. It's the original continent, basically the original continental rock, super old stuff. So that is to say that all these different colors represent younger materials that have been plastered onto the side of the continent. All right. Now to understand why mountains rise and why they become shorter over time. Okay, so you may wonder, why is it that mountain ranges don't just keep getting higher and higher if they're at a convergent plate boundary? Okay, if there were no forces at play, well, I guess mainly by that I mean gravity, then that would probably be possible, where mountains would just continue to rise upward. But in a world where there's a combination of gravity and weathering and erosion, what happens is over time, as a mountain belt is being constructed, as it's being lifted upward, what's concurrently happening is you have Mother Nature taking a hammer and a chisel to the existing rock above the surface. So you basically have the weathering and erosion processes simultaneously occurring, and what's happening is it's stripping away chunks, little sediments of the mountains, and moving those sediments away. And what that's doing is that will reduce the weight, the overall weight of the mountain belt. Okay, and typically what happens is during a mountain building event, what you'll see is what's called a root will develop. That's this kind of U-shaped feature down here at the bottom of the continental crust, that kind of blip that sinks down into the mantle right here. So the higher the mountain belt gets, the deeper the root gets. Think of the root as the foundation of the mountain range. And so, like I said, even while the mountain is building, weathering and erosion already occur, and they're kind of offsetting that. Okay, so as weight gets shedded off the mountain, okay, what happens is as more and more erosion occurs, you start to see the root start to lift up out of the mantle. Okay, and that's a process that's called isostasy. Well, actually, isostatic adjustment. So isostasy is basically an equilibrium that I just talked about, that balance that occurs between mountain uplift and the weathering and erosion processes that occur at the mountain that's above the surface. Okay, isostatic adjustment is like a ship, a cargo ship here, where when it has no cargo and it's empty, you'll notice that the ship rides up higher in the water. But then when you add a whole lot of cargo, the ship will ride closer, further, it'll ride further down in the water, okay? So that same concept is what happens here with isostatic adjustment. When you take the weight off, the object, which in this case is a mountain range, will, or the root rather, the root of the mountain range, the root will begin to rise up higher into the mantle, okay? And just so you know, this is the asthenosphere that we're talking about here. Where it says mantle, it really should say asthenosphere. Okay. So I think I beat that one to death. Are there any questions on on isostasy? Okay. All right. So that is kind of mountain building in a nutshell. So really not that awful complex when you really break it down. So then let's go ahead and shift gears here and start looking at surface processes. So these are things that you can actually observe readily on Earth's surface, okay? So I've mentioned weathering and erosion quite a bit, throughout everything that we've talked about so far. And if you might recall, in chapter 1, I showed this exact slide because it was such an important process that you needed to have a basic understanding of what it was before we got to this chapter. Okay, but I'm just going to go ahead and go through it again. So weathering is the disintegration or breakdown of rock at Earth's surface. Okay, whoops. Erosion is the transportation of that broken down material. So weathering is a hammer or a chisel. Erosion is like the truck that's carrying that material away to some other location. So there's two different types of weathering that we're going to look at. There's mechanical and chemical. So mechanical is the breakdown of rocks or earth material into smaller pieces by non-chemical forces. Okay, so AKA physical forces. So the main one is called frost wedging, and you see this one around this time of year. It rears its ugly head pretty consistently. This occurs as a result of the freeze-thaw cycle. So on these late winter, early spring days, oftentimes what will happen is you'll get above freezing temperatures during the daytime, so above 32 degrees. At nighttime, the temperatures will go down below freezing. Okay, so what's happening here is during the daytime, what was ice that earlier that night will melt, turn into water. That water will find any cracks or crevices in the area, and then we'll run down them. Okay. Come that night, that water will turn back to ice. So what you have is essentially water in these cracks turning into ice, and because there is about a 10% increase in volume when water turns to ice, which you've probably noticed from your freezer. That 10% increase in volume is what is used to pry rocks apart. So basically, the concept of frost wedging, you're just getting water in there to freeze and just wedge apart small cracks to become larger cracks. And yeah, I'll just leave it at that. So the cracks just become increasingly larger. You're most familiar with this concept with potholes, because potholes form the same exact way. where on these late winter days where the temperature might be above freezing, the ice will melt during the day, run down into cracks in the roads, and then freeze that night, widening up the cracks. And then as cars run over those widened cracks, they start to chip away at the asphalt, and eventually you end up with those honking craters. So, geology at work. All right, then there's another concept called unloading. So unloading is a reduction in pressure that's applied to buried rocks as those rocks come closer to Earth's surface. So you might be asking, why would a rock come closer to Earth's surface? Or why would a buried rock deep down? Typically mountain building is the main reason. And often what will happen is you see this thing called a pluton. That's essentially just what was a very deeply buried, solidified blob of magma. Okay, so it was a big blob of magma, and then it solidified and is now an igneous rock. Okay, these tend to make up the cores of mountains. These types of plutons. But anyways, either as a result of mountain building or as a result of weathering and erosion at the surface, what you see is essentially the material on top of this pluton gets stripped away for whatever reason, weathering and erosion, and what you're left with is that the pluton is now at Earth's surface. So because these plutons formed at a location where there was a lot of pressure pushing against them, when they get shoved up to Earth's surface into a low pressure environment, cracks will start to form, or joints, if you will. Okay, and that concept of these cracks forming is called unloading. So when you reduce the weight that's being pushed against it, and that is unloading. Okay, so it's unloading. So unloading is just reducing the weight. The cracking itself is technically called sheeting, but no need to separate those two for this class. So if you go to the mountains, oftentimes you'll see this. It looks like huge sheets, flat sheets of rock in the mountains. That's the end result of unloading. Another example of physical weathering is biological activity, which is actually quite important. So animal burrows, which is called bioturbation. Basically, you get critters like gophers or whatnot. They're digging their tunnels and burrows. What they're doing is they're loosening up the soil and aerating it. So that's actually very productive. That's good. That's good for the soil to do that. But what it does is, since it loosens up the soil, it makes it more prone to erosion. So it's kind of a double-edged sword. Tree roots. Oftentimes in the mountains as well, you'll see tree roots, or you'll see trees hanging on to sheer cliffs. And you're wondering, how the heck are they staying up there? Well, the short answer is that they have very good root system that is taking advantage of cracks or joints within the rock. So the tree's roots will, dig deep down into these joints. Okay, they'll to hold on to whatever they can. And as the trees get bigger over their lifespan, the roots get larger, and that creates basically assists to continue prying those rocks apart. So basically the roots will grow bigger and pry the rocks apart. So there's a couple instances of biological activity. Chemical weathering. So chemical weathering, of course, is the breakdown of rock caused by chemical reactions. So in chemical weathering, basically what you're having is chemical alteration of the internal structure of the minerals. So typically the mineralogy. Okay? And this occurs by typically by removing or adding elements, various elements. So in terms of chemical weathering on Earth's surface, water is definitely the most important agent. Typically, water is the medium that drives most chemical weathering here. All right, so those are the two, and actually, you know what, let me give you an example of chemical weathering. Okay, so caves are essentially a type of chemical weathering because you have the chemical breakdown of calcite in the limestone, okay? So what you have is acidic water, slightly acidic surface water, coming into contact with the basic calcite, and essentially the acid will eat away at the calcite. So this is what's called dissolve it. So it eats it and turns it into a dissolved constituency. That's just one example of many. Okay, and then lastly, you know, when you add together both physical and chemical weathering, the end result is essentially just the continuous breakdown of earth material into smaller and smaller pieces. So over time, what happens is you have large pieces of earth material. Okay, as erosion and weathering and erosion occurs, big chunks get broken down into smaller chunks. Those chunks get broken down into even smaller chunks. And what's happening is with each step, you're increasing the surface area of the earth materials. Okay, and so by the time you get down into all these little dinky chunks, each one of those has 6 sides, and those 6 sides are all now available for Mother Nature to attack, versus this big chunk. It still has 6 sides, but it's 6 huge sides. Everything inside of this huge chunk of rock is unable to be weathered because it's locked away from being weathered, basically. So once you start to get things really broken down and increase that surface area, that's when you start to see the earth material really start to break down really quickly. So here are some factors that determine the rate of weathering. So the mineral composition, of course, and any physical features like joints, okay? So if there's any pre-existing cracks, that is definitely going to facilitate weathering. Climate is also very important. So temperature and moisture are definitely the most crucial when we talk about climate. So chemical weathering is the most effective in climates that are warm and moist. Okay, so think tropics, southeast U.S., even the Midwest, where we get pretty warm, moist summers. Okay, so those are areas where weathering is it's quickest. Now on the flip side, actually, I guess I don't have that. On the flip side, it is cold, dry environments that are the most resistant to weathering. So places like deserts and Arctic regions, not a lot of weathering happens in those locations, honestly. And that is due to the dry and cold temperatures. Okay, so are there any questions on anything before we move on to a different subject? Okay. All right, so then let's take a look at soil. So soil is basically just a combination of mineral material, so broken down earth material, weathered earth material, air, water, and organic matter. So organic matter, which makes up about 5%, is made up of basically carbon materials, things that will decompose. So fertilizers, leaves that fall off trees in the fall, they will eventually fully decompose and become organic material. Critters and bugs that die, they will decompose and be turned into organic matter. Mineral matter, of course, you can see is about half of soil. So just broken down earth material. Okay, that's all it is. Very fine, broken down to the point where it's very fine. And then the other half is equal parts air and water. Okay, and those two are they're pretty critical. Soil, of course, has to have water for plant life, but air is equally important because air allows both space for water to get into if it needs to, and it also allows empty spaces where roots can grow into. Okay, if soil's super packed, it's hard for plants to develop a good root system. So it's really important that soil has a good percentage of air pockets found within it. Okay, so some controls of soil formation. Topography is probably the most important, and really, I guess that gets broken down into the steeper the terrain is, the less likely you're going to have soil on it. And that's because soils just are not they're not very well adept to develop on very steep slopes, because they just have a tendency to not be able to hold on very well. Okay, so that's why you don't see soils in very steep mountain environments a lot. So optimum is flat or hilly. Okay, I think Midwest. And orientation also plays a role as well. So when you have a slope that's faced southward, you're going to get the heat of the sun. So that means that the soil on the south slope is going to be typically warmer and drier. Okay, north slope, where the sun does not directly face at any point during the day, the soil is going to be moister and cooler, and those conditions are a little bit better for growing things. So for what it's worth, I guess it's just kind of more like a factoid, but it's something interesting. If you're trying to grow anything, that can actually come in handy. So take it as you will. Other controls of soil formation, of course, the parent material, what it's made out of, that matters as well, because some material just creates more of a richer soil than other types of material. Climate, we already talked about, the optimal being wet and warm type climates. And then, of course, the amount of organic material, okay, that plays a role. So the amount and extent of burrows, so bioturbation, adding fecal matter, fertilizer, stuff like that, decay of animals, trees, leaves, whatever. All that stuff is going to affect the substance of soil. Typically, the more organic material you add, the richer and more productive the soil is going to be. So this is a kind of a cutout look of soil structure. It's called a profile. Okay, so we're looking at a profile of soil from the side, and each one of these layers are called a horizon. And basically, these two top horizons, this blackish one and then this dark brown one here, those are referred to as topsoil. They're the most productive horizons. Those are typically made of organic material and then some mineral material. But typically, the O and the A horizons are made out of organic matter, and then further down, decaying organic matter mixed with mineral matter. Okay. These other horizons aren't really as important. They're basically just less productive layers that are more primitive. Whereas these layers, the O and the A horizons, are heavily influenced based on the surface material, because the surface material will eventually what's called leach. It'll the rain will drive the material downward through the soil layers. But down here, these are more primitive, more rock-like. They're more like the parent rock. So the B horizon is all mineral matter. This E horizon here, that's gray, that contains a lot of clay minerals that were leached. That's only associated with forested lands, which is kind of the unique thing about that. So farmlands don't have this E horizon. And then the C horizon here, you can see, is basically it's basically a parent material that is currently breaking down, currently being weathered into smaller material. So you can see little chunks that are eventually going to get fully broken down. And then you have the unweathered parent material here at the very bottom. Okay, so it's kind of a unique way this happens. Okay, so just pretty much what I just said. Okay. Okay, are there any questions on soils before we move on to a different subject? Okay. All right, then our last topic of the day is called mass wasting. This is just a fancy term for the downslope movement of earth materials under the influence of gravity. Okay, so these are things like rock falls, landslides. You're probably familiar with that term. Those things are both considered mass wasting. So some of the most important triggering factors that will trigger mass wasting, I'd say the most important factor is water saturation. So typically when soils become oversaturated, what happens is the individual soil grains are no longer in direct contact with each other. They find themselves where there's water in between the grains. And that means that they've lost control with, they've lost contact with each other, and thus, because gravity pulls things downward, once they lose contact with each other, gravity naturally is going to cause them to pull downward. And so that results in material moving down slope. So that's pretty typical on oversteepened slopes. You really don't see it on pretty flat slopes, because even if flat areas are happen to become oversaturated, nothing will happen because there's not enough gravity is not powerful enough to overcome the friction of the flatness. Okay. Some other things that often cause mass wasting: removal of vegetation. So this is also an erosion control issue, where, you know, you can see here in these pictures, here we have a very steep hill slope that was cut out to build this house. And believe it or not, this type of stuff happens all the time. And they shouldn't have built this house here, where they basically cut back into this cliff and they left an exposed, very steep hillside. Well, when it rains a lot, they're risking this steep hill slope becoming oversaturated and then giving way. Okay, and that's what happened in this picture down here. This is a process called slump that we'll see here in a couple of slides. Basically, the hillside is just rupturing and moving downhill under the influence of gravity, and it's taking this house with it. So I hope they had insurance there. Earthquakes as well. Earthquakes will shake the ground, and so if you already have a highly saturated soil, it may just be barely hanging on, okay? Just on the cusp of mass wasting, but not quite there. When you add that ground shaking, bam, that will trigger the final collapse. So that's pretty common in mountainous environments where earthquakes will actually trigger a lot of landslides. Okay, so we're going to look at a couple other types of mass wasting here in a minute, but before we get to those, I want to talk about this concept of angle of repose because this will apply to them. So the angle of repose is just simply the steepest angle in which a material, earth material, will remain stable before it mass wastes, okay? So you can see the sand pile here, or whatever it is. They're showing you its angle of repose. So this sand is piled up, and naturally it piles up to its angle of repose. That's just what earth materials do. And so if they were to saturate this pile because it's at its angle of repose, so if I get a lot of rain, this pile could potentially mass waste, but probably not. I mean, usually they're pretty benign. But really, where this kind of example can be best exemplified is with sand. So if you go to the beach and you try to build a sandcastle, you can't build a sandcastle with dry sand because it's not cohesive enough. You can't pack it together. Okay, those individual sand grains will just fall apart. Now you can't build a sandcastle with wet sand or, fully saturated sand, because you know that that's kind of mud-like. It won't stay up. But there's that perfect medium of damp sand where there's just enough water that coats these individual sand grains, where the water will actually create an electrical attraction to the adjacent water. Okay, so you see just these thin films of water surrounding the sand grains. The water atoms are being electrically attracted to each other. So it's kind of like they're holding tight, holding hands, and they're also holding on to the sand grains as well. So it's actually providing a very, very cohesive strength. We get a question here. Let me check. Yes. Okay, so yeah, the question is which material has the greatest angle of repose? Yes, there's multiple correct answers. Damp materials, yes. So even just damp mud, just barely wet, you can smash it together into forms, okay? But too much and it turns into mud. The other answer is that the greatest angle of repose, well, it really depends on the individual material, okay? And I guess I don't really want to get into that. If you Google angle of repose for earth materials, it'll bring up a list of various materials that you might encounter, like sand, clay, boulders, mud, whatever, and it will tell you what its angle of repose is. And you might be kind of surprised, but the overarching conclusion is that the angle of repose is really dependent on a couple different variables, and those variables are yes, water content, and then size of the material, and then shape of the material. Okay, so I will leave it at that. You're welcome. I'm glad to be here to explain these things. Hope you guys enjoy this as much as I do. This is my area of expertise. I've always loved surface processes. Okay, so that's the sandcastle concept. So that really kind of plays into these last forms of mass wasting. They're really broken down into a couple different categories. You have falls, slides, and flows. So falls in general are basically where you have, typically we're talking about big chunks of rock, like mountainous material, where you're in the mountains and you see a huge boulder just fall off the cliff, just detach itself from its adjacent rock. That's what a fall is. So it's a free fall of something consolidated, something that's a solid. A slide is this one here, where you still typically have a pretty cohesive material. It's pretty consolidated still, but it slides downhill typically as a kind of cohesive mass. The key here is that there's this thing called a rupture surface. That's the point of weakness. So this is just some layer where there was a weakness, and basically gravity overtook friction. There's more gravity, had a greater pull rather than the force of friction. Okay, and again, typically when we talk about mass wasting, usually we're talking about excessive water is what often triggers these things. So that's a slide. Those get broken down into a couple categories based on the type, or rather size of material. So the rock slide contains basically just big chunks of bedrock that just kind of slide down the mountain slope. Debris slide is kind of like what this is. It's a no, I guess this is a rock slide. Those are rocks. I was thinking that was vegetation, but no, it's not. So a debris slide is kind of a jumbled mess of everything that you would expect in like a forested region. So soil, rocks, trees, plants, perhaps the animals living in those things. I don't know. I'm sure they would go along for the ride. Basically a jumbled mess of every type of earth material of all different sizes. So that's a debris slide. Now there's flows. Flows are material that basically behave like mud. So they move as a viscous fluid. So we have debris flows. So that's movement of consolidated or unconsolidated materials. Typically the larger materials, but there's a lot of water. So again, it's typically bigger stuff, but it's like bigger stuff encased in mud, large amounts of water. And then lastly is the mud flow or earth flow. So these tend to be very fine-grained materials. So this literally is a mud flow. So it's like having a big wall of muddy water rushing down a mountain stream. Okay, you've probably seen pictures on the news or whatnot of that happening. Those can be quite destructive. Okay. And then we get to the last couple ones of examples of mass wasting. So slump, you can often see these in farm fields, especially where like pasture areas where cows graze. Cows have a tendency to create slump a lot of times because they weigh a lot. There's a lot of weight on their forelegs. Okay, so you put a lot of weight on an individual leg. That when you have a lot of rain, their weight can cause this slump appearance. And it's just simply there's a kind of a sideways C-type shaped rupture surface that you can see right here. And what happens is, as the rupture occurs, kind of a terrace formation occurs, where you get these individual terraces that rupture individually, but they all rupture in that C-type shape. So it looks kind of terraced. So if you see that terraced feature in farm fields, you'll know that that is a form of slump. Typically slump will occur in steeper slopes, as you would expect. Then there's creep. Okay, creep isn't as observable, like it doesn't happen fast. Creep is a very slow process, but it's probably the most observable. Okay, and creep is just simply downhill, very slow, gradual downhill movement of soil, basically. Sometimes we say regolith, which can be like soil plus any material that might be mixed in with the soil, like pebbles, maybe tree branches or tree trunks. Could be all sorts of stuff. But anyways, what's happening is typically this is associated with the freeze-thaw cycle. So like when we looked at the concept with the potholes, similar thing is happening where you have water infiltrating down into the soil. Okay, it'll freeze at night, that'll expand, cause an expansion, and that'll move the individual soil grains in a downhill fashion. Okay, and remember, when I say downhill, they move downhill because of gravity. Okay, so they'll move in the downhill fashion. The next day that ice will melt, turn back to water. Okay, and then that releases pressure against the soil, so the soil might move back a little bit to kind of readjust. Then the next night it reoccurs. So what you're seeing basically is this very slowly movement downhill over time as a result of the freeze-thaw cycle. Okay, so creep emanates as tilted fence poles, tilted utility poles. Tilted trees are less common. I mean, I rarely see that, but here in the Midwest, tilted utility poles, oh yeah. Fences around farm fields, those stakes are not put in crooked, okay? When they're built straight up and down. But if you notice, look closely, the stakes, when they creep, or when they're going with the creep, the top of the stakes is going to be pointing in the downhill direction, okay? Because that's how creep works. Another thing that you might see sometimes is like retaining walls that begin where the top begins to kind of hang over the bottom. So also, if you've ever been to a cemetery where it's on a hill, a lot of times the really old headstones, they got to be old because this just takes a long time for this process. You'll see the headstones leaning in a downhill direction. they've been subject to creep as well. So lots of lots of instances where you can see creep, we can see the effects of creep, but you will never actually see the creep itself. So one of those really interesting processes. All right. So the last form of mass wasting, last major form, is called solifluction. So this occurs in the Arctic and tundra and boreal forest areas, so the colder, drier climate areas on Earth. This is where we have what's called permafrost. That is permanently frozen soil, okay? And above that permafrost, or well, at the very top of the permafrost, is soil that will briefly de-thaw during the short summer months. Okay, and what happens is that's called the active layer. So the active layer will essentially move, or it can creep. The soil will creep on top of the frozen permafrost layer. So creep downhill as a result, again, of the freeze-thaw cycle. But like I said, this occurs only in the Arctic, well, not Arctic, I guess, tundra areas, yeah, because the Arctic areas typically have ice, glaciers. So yeah, if you go up to like Alaska, you'll see this. You'll see effects of solifluction. Okay, it kind of looks like terracing or layers. All right. So that's it. Are there any questions on anything that we covered today? Okay, I'll take that as a no. So then we will reconvene next Wednesday, and we will cover Chapter 9, Surface Water and Groundwater. Okay, so everybody have a good weekend. Enjoy the heat wave that we're having, and I'll see you on next Wednesday.
Have a good one.
Bye. Thank you. Have a good one.
Thank you.